Welcome back, everybody, to FP 101, Functional Programming. And today we're going to talk about types and classes. As developers, we often work all-nighters, we sit and hack, we get into a flow, and we lose track of time. And so for developers, it's extremely important to watch our diet to make sure that we eat well. If you see the food pyramid here that is shown there, food is grouped into categories. For example, you see bread, rice, and pasta, which are carbohydrates. And then you see other things like proteins, fruits and vegetables, etc. So all food is put into groups that have a common property. And in some sense, these groups, what we can say, is that the food here is typed. And that's what this lecture will be about. The lecture will be about taking values, not food, but the values that we code with, and how to group these into categories that have similar properties. So what is a type? Well, a type is simply a name for a collection of related values. Just like a food group is a name for a collection of foods with related properties, a type is a name for a collection of values that we code with that have similar properties. For example, in Haskell, the type bool is a name for a collection that has two values, false and true. Now, if we would be really, really pedantic in Haskell, there would be a third value, bottom, that represents a non-terminating computation of type bool. But in this course, since we're going to stick to the basics, we will ignore the more complicated features like bottom. So for now, we will just say bool is a type that names the set of values true and false, the Boolean values. Now, a type error is something where we're using a function with a type that the function does not expect. Let's look at the example here. If we want to add 1 to false, obviously that's not going to work, because on the left we have a number, and on the right we have a Boolean, and there's no way to add a number to a Boolean. Now, to go back to the example of diet, if you have a certain diet, maybe you're not allowed to mix meat and dairy products. So that would be a type error in the food world. And in the programming world, we have the same kind of type errors. And the goal of static typing is that the compiler will catch these type errors early on, before we run the program. But there's also dynamically typed languages where these type errors are caught at runtime. So when you're actually trying to add up the Boolean with the number. And then there's non-typed languages where this will just take however these two values are represented, and it will try to add them up. The notation, the syntax for writing down types in Haskell is expression : type. So if evaluating the expression E will produce a value of type T, we write this as E : T. Other languages have different syntax. For example, in Visual Basic, you will write E as T. In Java, you would write T E. But that's all syntax. So the real thing is that we're interested in the semantics of this, which says that the type of expression E is T. Now, every well-formed expression, every syntactically well-formed expression has a type, and that type is calculated by the compiler at compile time using a process called type inference. And remember from the first lecture that ML, the programming language ML, was one of the first programming languages that had type inference. Type errors are also in Haskell found at compile time, and most programming languages are found at compile time. And that, the opinions about differ, whether you have to have static typing or dynamic typing or optional typing. But for me personally, I'm lazy, so I like if the compiler catches the type errors for me early. In the previous lecture, we have played around with GHC, and GHC has a special command, :type, that allows you to ask the type of an expression. So you can ask GHC to calculate the type of an expression for you. So for example, if we type in not false, GHC will calculate the value of that, so not false equals true. But we can also ask for the type of not false, and in which case it will not evaluate that expression, but it will just calculate its type. So the type of not false is bool. And now we see that the value of not false is true, the type is bool, so that's consistent. So GHC did a good job. It would be weird and wrong if the type of not false would be integer, say, but the value would be true. So that is called type soundness, which means that the type that the compiler calculates corresponds with the value that this expression has when you execute it at runtime. In Haskell and in most programming languages, there are a number of base types. So these are types that are built into the language. And in Haskell, there's a handful. We have already seen bool, so the type of Boolean values, true and false. Then there's the type of characters. So the char is the name of a set of values that denote characters. So char contains characters like A, B, C, etc., all Unicode characters. Then there's the type of string, which are strings of characters. And we will see later that in Haskell, strings are really nothing more than lists of characters. So string, you could say it's not really a base type because it's defined in terms of two other base types, strings and characters. Haskell is unique, Python has similar properties in that it has both int and integers. So ints are fixed precision integers, 32 bits or 64-bit integers, and then integer are arbitrary precision integers. So you can compute the factorial of 500 if you use type integer. That will take a long time, but it will not overflow like when you use int. And then, of course, there's float, the floating point numbers. I mentioned when we talked about characters, I mentioned that strings really are lists of characters, and the type of lists is the first generic type or polymorphic type that we will see in Haskell. And a list is a sequence of values where all the elements have the same type. The first example here is a list of 3 booleans, false, true, and false. And you see here that we denote the type with : and then the type is list of bool. One of the nice features of Haskell is that the syntax of types, you see here the syntax of types, the syntax of values here on the left, looks very similar to the syntax of types on the right. So we use the same square brackets to indicate a list of values, and we use the same square brackets to indicate the type. So false, true, false has type bool. The second example there has a type, has a list of characters, A, B, C, D, and its type is a list of character, and that's just the same as string. So in general, the rule is that square brackets of t, list of t, denotes the type of lists with elements of type T. Now note that the type of a list doesn't say anything about its length. So if we have the list false true, it has type list of bool. And if we have the type, the value false true false, it also has type bool. And also, the types of these elements can be arbitrary as long as they're all the same. So the last example down here has a slightly more complicated type. It's a list of characters. So that's what you see here, list of characters. And if you look at the value, you see that it contains two lists of characters. But the thing with a list is that all the elements must have the same type, but the length is unrestricted. Compare and contrast that with tuples. A tuple, there the type contains the length, but the values, the types of the values can be different. So the first example here, that's a tuple of two booleans, true and false. So there you see that the type is bool, comma, bool. So it's not a list. If it would be a list, the type would be list of bool. But in this case, it's a tuple of two booleans, true and false, and the type is bool, bool. Now the second example there has type bool, char, bool. And what you see here is that it contains three values. One is a boolean, the second one is a character, and the third one is a boolean again, and that's reflected in the type. And in general, if we have a tuple of type T1 to Tn, that's the type of a tuple that has n values of each respective type T1 up to Tn. So the type of a tuple encodes its size. So true, false, or false, true there has a type bool, bool. So you see there that the length of this tuple is reflected in the type. Second one there, there's three booleans. So we see that the tuple has three booleans. And the type of the values is unrestricted, so they can be mixed and matched. So in this case, we have a tuple that contains a character, and then as the second value, a tuple that has a boolean and a character. And then the last example there is a tuple that has a boolean and then a list of characters. So you see, there's a boolean here, a boolean, true, and a list of A, B, and we see that the type there is bool and list of char. So this is the end of part 1 about types, and next we will talk about functions. Since we're dealing with a functional language, functions are very important, so we'll spend a little bit of time zooming into functions. Thank you, and see you after the break.